In the heart of Vienna, on a quiet day in August 1887, a child was born who would one day question the very foundations of reality itself. His name was Erwin Rudolf Joseph Alexander Schrödinger. The city he was born into was a place of elegance, art, and intellect, a world where classical music floated through the streets and philosophy filled the cafes. It was the cultural capital of the Austro-Hungarian Empire, a melting pot of ideas, debates, and dreams. In this vibrant world, young Schrödinger's mind began to take shape, guided by curiosity that reached beyond the ordinary. From his earliest years, Erwin was not a child easily satisfied with simple answers. He had an intense hunger to understand why the world worked as it did. The colors of the sky, the whisper of the wind, the silent rhythm of falling leaves. Each seemed to him like coded messages from nature, waiting to be deciphered. His parents noticed this sensitivity early on. His father, Rudolf Schrödinger, was a botanist and a passionate amateur scientist who filled their home with books and instruments. His mother, Georgian Amelia Brenda, came from a family that valued education and art. Together, they created an environment where learning was not a duty, but a way of living. Erwin's father became his first teacher, showing him the beauty of observation. He taught him to question every assumption and to find the harmony that lay behind complexity. In their modest home laboratory, they studied plants, minerals, and physical experiments. These early lessons planted in Erwin a belief that nature was not chaotic. It followed deep, elegant laws, even if those laws were hidden from plain sight. The child learned that knowledge is not memorized, it is discovered through wonder. As he grew older, Schrödinger's curiosity stretched far beyond the boundaries of school lessons. He was fascinated by philosophy as much as by mathematics. He read widely: Goethe, Schopenhauer, Spinoza, thinkers who blended logic with imagination. He saw in their writings a common theme: reality was not merely what we see, but what we think about what we see. This dual fascination, of mind and matter, would later become the backbone of his scientific worldview. When he entered the University of Vienna in 1906, the world of science was standing on the edge of transformation. Physics, which had once seemed complete and logical, was beginning to tremble under strange new discoveries. The electron had been found, X-rays were puzzling scientists, and the idea that light could act both as a wave and a particle had begun to challenge traditional logic. Schrödinger entered this world not as a mere student, but as a seeker. His professors taught him the equations of classical physics, but his mind was already moving toward the mysteries that equations could not fully explain. At the university, Schrödinger's brilliance quickly became apparent. He excelled in mathematics, mastering the rigid structures of analytical mechanics and differential equations. Yet, he found in mathematics not just a tool but a language, a poetic bridge between the seen and the unseen. He began to realize that mathematics could express the rhythm of the universe just as music expressed the rhythm of the soul. The precision of numbers for him was never cold, it was alive, filled with mystery and beauty. But what truly set Schrödinger apart was his refusal to think in straight lines. While other students memorized formulas, he asked what those formulas meant. When his teachers discussed Newton's laws or Maxwell's equations, he wanted to know what they revealed about the essence of reality. This deeper questioning, this demand for meaning, became a lifelong habit. He could not accept a theory that did not feel intuitively complete. It was not enough for him that mathematics worked. He wanted to understand why it worked. During his student years, Schrödinger developed a quiet but powerful independence of thought. He was influenced by his mentor Fritz Hörl, who was exploring the connection between radiation and energy, an idea that hinted at Einstein's revolutionary theories. Hörl's teaching left a mark on him, showing that even the most solid physical laws could be reshaped by new insights. Schrödinger absorbed this lesson deeply: science must always evolve, and no truth was too sacred to be questioned. Then came World War I, a storm that swept across Europe and changed everything. Like many young intellectuals of his generation, Schrödinger was drawn into the war. He served as an artillery officer in the Austrian army, facing the chaos and destruction of the front lines. Amidst the cold and violence, his mind remained restless. He carried with him books on mathematics and philosophy, reading them in rare moments of calm. The contrast between the senselessness of war and the order of science sharpened his longing to find meaning in a world that seemed to have lost it. The war ended in 1918, leaving behind ruins, not only physical but intellectual. Europe's faith in reason had been shaken. For Schrödinger, it was a time of rebuilding, both personally and scientifically. He returned to academia with renewed determination, seeking to understand the invisible principles that governed the universe, principles that perhaps could reveal a deeper order behind the apparent chaos of life. During the early 1920s, as quantum physics began to rise from the minds of pioneers like Planck, Einstein and Bohr, Schrödinger found himself both fascinated and unsettled. The new theories described a world of probabilities, not certainties. A universe where particles did not have definite paths, but rather existed in clouds of possibility. For a thinker like Schrödinger, trained in logic and beauty, this probabilistic world was both thrilling and disturbing. He admired the success of these theories, but resisted their philosophical implications. He still believed that beneath the strangeness of quantum phenomena, there must exist a smooth, continuous reality, one that could be expressed through waves, not jumps. This conviction did not appear out of nowhere. It was born from his early education, the blend of scientific rigor and philosophical introspection he had cultivated since childhood. His curiosity was not just about equations but about existence itself. He believed that the universe was an organism, not a machine. Each part was connected to the whole in ways human perception could barely grasp. His unique upbringing had also given him the courage to challenge authority. Vienna had taught him to appreciate individuality of thought, his father had taught him to experiment, his books had taught him to dream. So when the time came to face the giants of modern physics, Schrödinger was not afraid to stand apart. He began to develop an alternative way of seeing quantum behavior, not as discrete, random jumps of particles but as continuous waves of energy that spread smoothly through space. In 1925, when Werner Heisenberg proposed matrix mechanics, a strange, abstract method of describing atomic behavior, Schrödinger found it too mathematical and detached from physical intuition. He longed for a picture that could be imagined, a model that captured the flow of reality as something tangible, and so he turned to wave theory. Inspired by de Broglie's idea that matter itself could behave like waves, Schrödinger began to work day and night, searching for a mathematical expression that could unite the new quantum discoveries with his vision of continuity. This pursuit was not merely scientific, it was spiritual. He once described feeling a kind of mental fever during the days when he formulated his famous wave equation. Every line of calculation was a bridge between two worlds, the world of logic and the world of imagination. It was as if he was listening to the silent music of the universe and trying to translate it into human language. The same curiosity that had driven the boy in Vienna now guided the man who would soon change the course of physics. Schrödinger's approach to science was unconventional because it came from the heart as much as from the mind. He believed that science without philosophy was blind, and philosophy without science was empty. This was the essence of his unconventionality. While most physicists of his time focused solely on measurable data, Schrödinger wanted meaning, a unified understanding that connected the physical with the metaphysical. He often wrote about the onness of existence, the idea that consciousness and matter were two sides of the same coin. To him, studying the atom was not separate from studying the mind that perceived it. This deep sense of unity and purpose can be traced back to his early curiosity, that childlike wonder that never left him. Even as an adult, he would sit in silence for hours, thinking about how a single particle could exist as a wave, or how reality could appear solid when it was actually fluid and uncertain beneath the surface. His unconventional approach was not rebellion for its own sake. It was the natural expression of a mind that refused to stop asking questions. He once said that the task of science was not to discover how the universe is, but to understand how we come to experience it as it appears. This insight shows how far his thinking extended beyond the laboratory. It reflected a philosophical depth shaped by years of reading and reflection, from the poetic philosophy of the East to the rational clarity of Western science. As he continued his academic career, Schrödinger became known not only for his brilliance but for his independent spirit. His lectures were unlike any others. He would move seamlessly from mathematics to metaphysics, from equations to existential questions. Students often described him as both a scientist and a poet. He would say that the universe was not a cold machine, but a living mystery, and that true science must embrace that mystery rather than destroy it. By the time he published his wave equation in 1926, Schrödinger had already become a symbol of creative rebellion in physics. His theory showed that particles could be described as wave functions, smooth, continuous expressions of probability that captured the dual nature of matter. This breakthrough unified the strange behaviors observed in the quantum world with the elegance of classical mechanics. But more than a scientific formula, it represented a triumph of imagination, the victory of curiosity over conformity. Behind this achievement lay the foundation built in his youth, the education that encouraged thinking instead of memorizing, the philosophy that taught him to seek harmony instead of fragmentation, the experiences that reminded him of life's unpredictability and beauty. All these shaped a mind that could challenge even the most established logic. Schrödinger's early curiosity made him a philosopher, scientist, a rare blend of intuition and intellect. His approach was not to dissect nature, but to listen to it. He believed that the secrets of reality reveal themselves only to those who approach them with wonder, not arrogance. In every experiment, every equation, and every paradox he faced, there was the echo of that young boy standing by his father's side, asking how the invisible forces of nature could be understood through thought and imagination. Even later in life, when fame surrounded him, Schrödinger often looked back at those early days in Vienna as the most formative time of his existence. He believed that the seeds of all discovery are planted in childhood curiosity, a curiosity that must never be lost, no matter how complex the world becomes. His unconventional approach, shaped by those early influences, remains a testament to the power of asking why instead of merely how. In the story of Erwin Schrödinger, the roots of quantum theory are intertwined with the roots of human wonder itself. The journey from a curious child in Vienna to a Nobel-winning physicist was not just a journey through science. It was a journey through the landscape of thought, from the boundaries of reason to the horizon of imagination. The young boy who once watched the sky in quiet fascination had become the thinker who challenged the logic of the universe. His early curiosity was not just the beginning of his story. It was the spark that ignited modern physics itself. When Schrödinger looked back on his youth, he often said that curiosity had been his greatest inheritance. It was not wealth or privilege that defined him, but the freedom to ask questions without fear of being wrong. That freedom shaped his spirit, and it became the invisible thread running through all his later work. To understand his scientific rebellion, one must first understand that it grew naturally from this soil of independence. After completing his university studies, Schrödinger began his journey through the academic world of early 20th century Europe, a world buzzing with new ideas but still chained to old structures. Laboratories were becoming temples of precision, where every measurement was treated as sacred truth. Yet Schrödinger felt that something vital was being lost. The deeper meaning of science, the human quest for understanding, was being overshadowed by an obsession with numbers. He respected mathematics deeply, but he feared that physics was becoming mechanical, detached from life's essence. His unconventional approach to science was, in many ways, a quiet protest against this mechanization of thought. His teaching style revealed this difference. When he became a lecturer, students found that his classes felt more like conversations than lessons. He would begin with a mathematical equation, but within minutes, he was speaking about the nature of consciousness, the structure of language, or the beauty of a sunset. For him, science and art were not opposites, but reflections of the same human desire to make sense of existence. He believed that a physicist who could not appreciate poetry would never truly understand the rhythm of the universe. In this period, Schrödinger also discovered the writings of Eastern philosophers, especially the Upanishads and Buddhist texts. He was captivated by their concept of unity, the idea that all living and non-living things are expressions of one reality. These ideas blended naturally with his early love of Western philosophy and created in him a worldview that was neither purely scientific nor purely mystical, but something unique, a holistic vision of reality. This spiritual dimension did not make him less of a scientist, it made him a deeper one. His wave mechanics, years later, would emerge from this synthesis of logic and intuition. When he began working on the mathematical description of waves, he was motivated not only by technical puzzles, but by a desire to restore continuity to physics. The quantum theory of his contemporaries described nature as fragmented, full of random jumps and discontinuities. To Schrödinger, this was unsatisfying. He wanted a universe that was smooth, elegant, and connected, a universe that could be grasped intuitively, not just statistically. His early training in classical mechanics and his artistic sense of beauty both told him that nature could not be that chaotic. It had to obey patterns that, while hidden, were fundamentally harmonious. This conviction pushed him into a period of intense work. The winter of 1925 in the Swiss Alps became legendary in his life. He secluded himself in a small cabin, carrying with him only his notebooks and his thoughts. Outside, snow blanketed the mountains in silence. Inside, a fire burned and equations filled the air like whispers of inspiration. It was during these days of solitude that he found what he had been searching for, the mathematical expression that described how quantum particles behaved as waves. When he finally derived the equation that bore his name, he felt a sense of profound peace. For a brief moment, he believed he had glimpsed the order behind the chaos. Yet even in triumph, Schrödinger remained a philosopher. He did not see the wave equation as a final truth, but as a bridge to deeper understanding. He often compared scientific discovery to climbing a mountain. Every peak revealed another, higher one beyond it. His curiosity was endless, his satisfaction temporary. He never stopped questioning what his own discoveries truly meant. After publishing his results, Schrödinger became an international figure almost overnight. The scientific world recognized the brilliance of his achievement, and he shared the Nobel Prize in Physics in 1933. But fame did not change him. In public lectures, he continued to speak of science in poetic language. He would tell audiences that a physicist must be humble before nature, that the universe does not reveal its secrets to those who approach it with arrogance. His voice carried both authority and warmth, a calm reminder that knowledge and wisdom are not the same thing. However, success also brought conflict. Many of his peers interpreted his wave mechanics differently than he intended. They saw it merely as a mathematical tool to calculate probabilities, not as evidence of an underlying continuous reality. Schrödinger protested this view, arguing that the wave represented something real, not just an abstraction. His debates with Bohr and Heisenberg became some of the most profound philosophical discussions in the history of science. At stake was not just a theory but a worldview. Whether the universe was governed by chance or by order. Schrödinger's early curiosity had prepared him for this intellectual battle. The child who once asked why leaves turned toward the sun now asked why electrons behaved as they did. The same fearless questioning that had defined his youth gave him the strength to challenge the mainstream of physics. Even when isolated, he refused to conform. His belief in the unity and intelligibility of the universe was unshakable. Beyond his scientific life, Schrödinger's personality remained as complex as his theories. He loved music, nature, and solitude. He would often hike in the mountains or spend long hours gazing at lakes, feeling that nature itself was a living equation. His notebooks from this period contain not only formulas but sketches of landscapes and reflections on existence. He wrote that, "The world is given to me only once, not one existing and one perceived." These words encapsulate his view that consciousness and reality are inseparable, a view that would later influence fields as diverse as philosophy of mind and biology. His curiosity also led him to venture into areas far from physics. In the 1940s he wrote What is Life?, a small but powerful book that explored how physical laws could explain the mystery of living organisms. In that book, Schrödinger predicted that genetic information must be stored in a stable, code-like molecule, an idea that directly inspired the discovery of DNA a decade later. Once again, his curiosity had guided him beyond boundaries, connecting the structure of matter to the structure of life. As the years passed, Schrödinger's thinking became increasingly philosophical. He began to see all scientific knowledge as a reflection of human consciousness. The universe, he believed, was not separate from the observer. It was a single system in which observer and observed were intertwined. This was a radical idea for his time, but it flowed naturally from his lifelong curiosity. The child who had once asked how the physical world worked was now asking what it meant for the world to be known at all. He often spoke of the limitations of human perception. To him, the senses were like narrow windows through which we catch only fragments of reality. Science, therefore, was an act of translation, an attempt to turn the infinite into the understandable. But every translation, he warned, loses something of the original. The true universe, he thought, might be far beyond the reach of language or mathematics. Still, it was worth pursuing, because the act of seeking brought humanity closer to its essence. This view of science as a spiritual journey was perhaps the greatest expression of his unconventional approach. Schrödinger saw no contradiction between logic and mystery. In fact, he believed they completed each other. Logic provided structure, mystery gave it meaning. Without curiosity, logic becomes empty. Without structure, curiosity becomes chaos. His life embodied the balance between these two forces. Even in his later years, Schrödinger continued to challenge accepted ideas. He questioned the growing separation between disciplines, between physics and philosophy, between science and the humanities. He urged young scientists to read literature, to study history, to travel, and to see the unity of knowledge. To him, the divisions humans created were illusions. Nature itself knew no boundaries. When he taught his final classes, his students remembered not just the content of his lectures, but the atmosphere he created. The feeling that learning was an adventure, not a routine. He would begin quietly, perhaps by writing a single equation on the board, then pause and look at it as though it were a line of poetry. This, he would say, is not just mathematics. It is a sentence written by nature herself. Those who studied under him often said that he changed not only their understanding of physics, but their way of seeing the world. In reflecting on his journey, one can see how every stage of Schrödinger's life echoed the first keynote. His early curiosity and education shaped his unconventional approach to science. The habits of thought formed in childhood became the compass that guided him through a lifetime of discovery. His openness to philosophy made him question the mechanical view of the universe. His sense of beauty made him seek harmony in equations. His independence of mind made him resist the tide of consensus. There is also a deeply human lesson in his story. Schrödinger's curiosity was not driven by ambition or the desire for fame, it was driven by wonder. He looked at the world with the eyes of a poet and the discipline of a mathematician. That rare combination allowed him to glimpse patterns others overlooked. He once remarked that, "The task is not so much to see what no one has yet seen, but to think what no one has yet thought about what everyone sees." This line captures the essence of his unconventional spirit. Innovation born not from new sights, but from new ways of seeing. In the closing years of his life, living quietly in Austria once again, Schrödinger often spoke about the continuity of existence. He believed that consciousness did not truly begin or end, that each individual mind was a wave in the larger ocean of reality. This belief, deeply rooted in his youthful studies of philosophy, gave him serenity. Even as his health declined, his curiosity remained alive. Visitors described him sitting by the window, reading, writing, or simply staring at the changing light, still exploring, still wondering. When he passed away in 1961, the world lost not only a scientist, but a thinker who had dared to question the foundations of logic itself. Yet his legacy continues to ripple through science, philosophy, and even art. Every time physicists discuss wave functions or the paradox of quantum observation, they are walking in the footsteps of the curious boy from Vienna who refused to accept easy answers. His life reminds us that curiosity is not a childish trait to be outgrown, but the purest form of intelligence. It is the flame that lights every path of discovery. Schrödinger's early curiosity was the beginning of a lifelong dialogue between mind and nature, a dialogue that continues through all who seek to understand the universe with both intellect and imagination. Today, when we speak of quantum mechanics, we speak in the language Schrödinger helped create. But behind every formula, there remains the echo of his deeper question, not just how does the universe behave, but why does it behave in this way? And can the same laws that shape atoms also shape thought, life, and consciousness? These are questions that still challenge us, and perhaps always will. In the end, Schrödinger's unconventional approach was not about rejecting quantum logic, but expanding it. He showed that logic must be flexible, that science must evolve, and that curiosity must never die. His journey from a child's fascination to a philosopher's insight is a testament to the boundless potential of the human mind. The story closes where it began, in the quiet of Vienna, with a young boy staring at the world in wonder. The questions he asked then have never truly been answered. They continue to live, resonating through laboratories and lecture halls, through the thoughts of every scientist who dares to look beyond the known. In every wave that rises and falls, in every mystery that beckons, the spirit of Erwin Schrödinger endures, the thinker who challenged quantum logic, guided forever by the power of a single, unending curiosity. In the mid-1920s, the world of physics stood at a crossroads. The comfortable certainty of classical mechanics, the universe of Newton, where everything moved in predictable paths, was breaking apart. Experiments with light, electricity, and atomic particles were revealing a strange, invisible world that refused to follow the old rules. Electrons jumped from one orbit to another without passing through the space in between. Energy seemed to exist in discrete packets, or quanta, rather than in continuous flows. For scientists who had grown up believing that nature was a smooth, logical machine, these discoveries were nothing short of disturbing. Among the thinkers staring into this mystery was a quiet, thoughtful Austrian physicist named Erwin Schrödinger. Schrödinger was fascinated by the new quantum ideas, but also uneasy about them. He admired Max Planck's revolutionary concept that energy was quantized, and he respected Einstein's insight that light could behave as both wave and particle. But he could not accept the growing belief that nature was fundamentally random. The so-called quantum jumps seemed too abrupt, too chaotic. Schrödinger's mind was steeped in the classical vision of harmony and continuity. To him, the universe was not a game of dice, it was a symphony. He believed that if the new quantum world seemed fragmented, it was because humanity had not yet found the right language to describe its continuity. He decided to search for that language. His search began with a question that had haunted him since he first encountered the strange behavior of atoms: if light, which had long been considered a wave, could also behave like a particle, could matter itself behave like a wave too? It was a daring idea, one that challenged the very foundation of physics, In 1924, a young French physicist, Louis de Broglie, proposed that all particles might have wave-like properties, their wavelengths determined by their momentum. This simple but profound hypothesis electrified Schrödinger's imagination. De Broglie had opened a door, but it was Schrödinger who would step through it and map the new world beyond. He began by asking what kind of equation could describe such matter waves. If an electron behaved like a wave, it should obey the same kind of mathematical laws that govern light and sound waves. These were well known from the field of classical physics, equations that described how waves propagated through space and time. Schrödinger started from these familiar forms and began to modify them, trying to make them fit the quantum world. His mind worked not in straight logic, but in patterns and pictures. He visualized the electron not as a small ball circling the nucleus, as Bohr's model had suggested, but as a vibrating wave spread out around it. The atom, in his imagination, became a standing wave, a resonance pattern where only certain wavelengths could exist, explaining why electrons seem to have fixed energy levels. This idea was as beautiful as it was radical. Instead of thinking about electrons jumping between orbits, Schrödinger proposed that their energy states were simply different vibration modes of the same continuous wave. The transitions between them were not jumps, but changes in the form of vibration, smooth, logical, and deeply harmonious. It was an idea that satisfied both his scientific rigor and his sense of aesthetic beauty. He worked in isolation, often through long nights, driven by a quiet obsession. In the winter of 1925, he retreated to the Swiss Alps, seeking clarity in the silence of nature. The snow-covered peaks and vast stillness gave him the peace he needed to think freely. Surrounded by the timeless rhythm of the mountains, he wrote equation after equation, searching for the one that would capture the essence of the quantum wave. Each calculation brought him closer to something profound, a unifying principle that could bring order to the apparent randomness of atomic behavior. At last, he found it. In early 1926, Schrödinger formulated an equation that described how these matter waves evolved over time. The equation was elegant, compact, and powerful, a mathematical structure that could predict the behavior of particles with astonishing accuracy. It became known as the Schrödinger equation, and it marked a turning point in the history of science. It was written in a form that physicists recognized instantly, yet it expressed a completely new vision of reality. The equation told them that particles were not isolated points but wave functions, entities spread out across space, carrying probabilities rather than certainties. To the scientific community, the impact was immediate and transformative. Schrödinger's equation offered a new way to understand atomic structure without relying on the arbitrary, quantum jumps of the old theory. It explained the spectral lines of hydrogen, the very fingerprints of the atom, with remarkable precision. What had once seemed mysterious now followed naturally from the mathematics of waves. It was as if a fog had lifted, revealing a hidden architecture behind the quantum world. Schrödinger's discovery changed not only the equations of physics, but also its philosophy. Before his work, quantum mechanics was fragmented, a collection of strange rules that worked but made little intuitive sense. With the wave equation, Schrödinger gave the theory coherence. He brought it back into the language of the continuous and the comprehensible. His mathematics reintroduced beauty into the chaos. Many physicists felt a sense of relief, as if nature had been restored to logical order. But even as his equation began to revolutionize physics, Schrödinger himself wrestled with its interpretation. He believed that the wave function represented a real, physical wave, something that actually existed in space, not just a mathematical abstraction. To him, the electron's wave was a tangible field of energy, vibrating continuously through space. But others, including Niels Bohr and Werner Heisenberg, disagreed. They argued that the wave function did not represent a physical wave, but merely the probability of finding a particle in a given place. According to their view, known as the Copenhagen interpretation, nature itself was probabilistic. and reality only became definite when observed. For Schrödinger, this was unacceptable. He saw it as a retreat from understanding, a surrender to mystery rather than a resolution of it. His equation had given him a glimpse of a universe that was elegant and deterministic, where waves unfolded according to precise laws. To reduce that beauty to a matter of chance seemed to him like an act of intellectual betrayal. He began to argue passionately that the wave function described something real, something that existed whether anyone was looking or not. This philosophical struggle would define much of Schrödinger's later life, but in those early years, before the debates intensified, the success of his wave mechanics filled the scientific world with excitement. Researchers across Europe and America began using his equation to calculate the properties of atoms, molecules, and even crystals. It worked everywhere they applied it, predicting results that matched experiments with astonishing accuracy. It became the foundation for modern quantum mechanics and eventually for the development of chemistry, electronics, and materials science. Every transistor, every laser, every quantum computer built today rests on the mathematics Schrödinger discovered in that alpine solitude. And yet, Schrödinger himself was never content simply to calculate. He was searching for meaning, for the connection between mathematics and reality. He felt that equations alone could not capture the essence of existence unless they spoke to something deeper. In his writings, he often compared the wave function to the patterns of consciousness itself, something invisible yet undeniably real. Just as a wave could exist in many places at once, he wondered whether the human mind, too, might be a kind of field that transcended the boundaries of the physical brain. Such thoughts made him both a scientist and a philosopher, a rare combination that sometimes puzzled his contemporaries but gave his work its timeless depth. His wave equation transformed quantum theory not only mathematically but conceptually. Before Schrödinger, the quantum world was seen as a collection of disconnected facts. After him, it became a dynamic field of relationships. His equation unified the microscopic and macroscopic views of reality. It showed that the behavior of atoms was not chaotic but guided by precise mathematical harmony. A harmony that echoed the same patterns found in sound, light, and motion. The sheer simplicity of the equation concealed its power. Written in symbols, it could fit easily on a single line, yet it described the entire quantum universe. Physicists would later marvel at how something so compact could contain such vastness. The equation's structure revealed that time, energy, and space were intertwined in subtle ways, governed by the constant of Planck and the mass of the particle. It was a doorway into the invisible architecture of matter. Schrödinger himself was aware of the poetry within his mathematics. He once said that the equation had come to him like a melody, that its form felt inevitable, as if it had always existed, waiting to be discovered. He often described the process of derivation as though he were listening rather than inventing. The work, he wrote, is not mine alone, it is nature herself who dictated it. This humility before discovery was part of his genius. He did not seek to dominate the world with knowledge, but to understand it as an artist understands form. By becoming one with its rhythm, as his fame spread, Schrödinger traveled widely, giving lectures and collaborating with other great minds. Everywhere he went, his wave equation became the central focus of discussion. Some physicists, like Paul Dirac, extended it further, merging it with the principles of relativity. Others used it to explain chemical bonding, solid-state phenomena, and even the behavior of stars. The universe, once thought mechanical and separate, now appeared interconnected and dynamic. Through all this, Schrödinger remained reflective, even melancholic at times. He sensed that the true meaning of his discovery was not fully understood, not even by himself. He was haunted by the question of what the wave function really represented. Was it a physical wave, a probability, or something beyond both? His mind oscillated between these interpretations, just as the waves in his equation oscillated between peaks and troughs. Yet he never lost faith that beneath the abstractions lay a deeper reality, waiting to be comprehended. In those years, he was often seen walking alone, lost in thought, carrying notebooks filled with equations and fragments of philosophical musings. To his colleagues, he was both a revolutionary and a dreamer. He had reshaped physics, but his gaze was always turned toward something even larger: the unity of knowledge. His wave equation had given scientists the power to calculate the unseen, but he wanted it to also inspire them to imagine. For him, imagination was not a luxury of science, it was its foundation. As the 1920s gave way to the 1930s, the implications of his equations spread beyond physics into the very concept of reality itself. It challenged the boundary between determinism and uncertainty, between matter and thought. Philosophers began to see in Schrödinger's wave mechanics a reflection of the dual nature of human existence, the coexistence of clarity and mystery. His work became a mirror in which both science and philosophy saw themselves anew. It is no exaggeration to say that Schrödinger's equation transformed human understanding of the universe. It turned atoms from mechanical entities into patterns of possibility. It revealed that solidity itself was an illusion, that every object, from a grain of sand to a living cell, was a vibrating field of probability waves. In that revelation lay both beauty and strangeness. The world had become richer, but also more mysterious than ever. And so, as Schrödinger looked at the equation he had written, he saw not just a mathematical triumph but a philosophical challenge. The universe it described was continuous, yet uncertain, ordered, yet elusive. It invited humanity to rethink what it meant to know something. For him, that was the true power of science, not to provide final answers, but to expand the horizon of wonder. Even as the Schrödinger equation began to gain recognition, Erwin Schrödinger himself continued to wrestle with its implications. He understood that an equation, no matter how elegant, is only a tool, a map of reality, not reality itself. Yet the beauty of this particular map was undeniable. For the first time, the strange behavior of electrons and other subatomic particles could be described in a coherent, continuous framework. Schrödinger's wave mechanics did not just explain experimental data, it offered a vision of the atomic world as a harmonious, interconnected whole. The electrons, once imagined as discrete particles jumping unpredictably between orbits, now appeared as rippling waves, their behavior dictated by the undulating patterns of probability. In laboratories across Europe, young physicists quickly recognized the utility of this new approach. Atomic spectra that had puzzled scientists for decades now fell into place under Schrödinger's formalism. Hydrogen, the simplest atom, could be described with unprecedented precision. Its energy levels, previously treated as arbitrary, emerged naturally from the solutions to the wave equation. The patterns of light emitted by atoms, the spectral lines that had been recorded painstakingly over the years, were now explained as natural consequences of resonant vibrations within the wave function. In this way, Schrödinger transformed quantum theory from a collection of isolated observations into a predictive, coherent science. Yet the transformation was not merely technical, it was philosophical. Before Schrödinger, quantum mechanics appeared fragmented, its rules a patchwork of oddities that defied intuition. With the wave equation, continuity returned. Nature was no longer a collection of abrupt jumps and inexplicable phenomena. Instead, it revealed itself as a flowing, wave-like system, governed by mathematical principles that could be visualized and understood. Schrödinger's equation allowed scientists to imagine atoms as miniature musical instruments, their energy states the harmonics of a vibrating string. The analogy was not merely poetic, it captured the underlying logic that the mathematics expressed. This conceptual shift had profound implications. It challenged the dominant interpretation of quantum mechanics at the time, particularly the probabilistic perspective promoted by Niels Bohr and Werner Heisenberg. While the Copenhagen interpretation suggested that particles exist in indeterminate states until observed, Schrödinger proposed that the wave function represented a physically real field. The electrons spread out, Wave was not a mere tool for calculation, but an actual manifestation of reality. To him, the world was fundamentally continuous, not discrete, and its apparent randomness was a reflection of human ignorance, not the universe's caprice. In the midst of this debate, Schrödinger also explored the relationship between his equation and classical physics. He recognized that his wave mechanics must reduce to familiar classical results in the limit of large systems. This correspondence principle, which connected quantum and classical domains, became a guiding principle for physicists. It ensured that Schrödinger's theory was not an isolated abstraction, but a natural extension of centuries of scientific understanding. In doing so, he bridged the gap between the mysterious quantum world and the intuitive macroscopic universe we inhabit. During this period, Schrödinger's work inspired others to explore new areas of physics. Chemists used the equation to understand the behavior of molecules, leading to the birth of quantum chemistry. Solid-state physicists applied wave mechanics to study crystals, paving the way for modern electronics and materials science. Even the nascent field of nuclear physics benefited from his formalism. In this sense, Schrödinger's wave equation became a foundational tool, a universal key to unlock the secrets of matter. Yet the man behind the mathematics remained intensely reflective. Schrödinger often wrote about the philosophical significance of his discovery, noting that the wave function could not be separated from the observer's consciousness. In his later essays, he suggested that the universe was not merely a collection of objects, but an interconnected whole, where knowledge and reality were intertwined. This perspective blurred the boundaries between physics and philosophy, suggesting that understanding the universe required not only calculations, but also contemplation. The practical impact of Schrödinger's equation was staggering. Experimental predictions that had once seemed impossible were now achievable. Physicists could calculate energy levels, predict molecular interactions, and even explore the behavior of electrons in complex systems. The wave equation provided a framework within which both classical and quantum phenomena could be understood. Its reach extended beyond the laboratory, influencing chemistry, engineering, and even the emerging field of computational modeling. Schrödinger had created a bridge between abstract mathematics and tangible reality, a tool that would shape the course of science for decades to come. Yet, for Schrödinger, the most profound transformation was personal and philosophical. The wave equation represented the triumph of his unique approach, one that combined rigorous mathematics with a deep sense of intuition and imagination. It was the culmination of years of curiosity, reflection, and solitary work. In creating the equation, he had fulfilled the promise of his early education, to seek understanding not only through measurement, but through insight, not only through facts but through the harmony underlying them. The wave equation also marked a turning point in the collective imagination of physicists. It invited them to envision a universe in motion, where particles were never truly isolated, but part of a continuous, dynamic field. Electrons were not tiny billiard balls, they were waves vibrating in a cosmic sea. Atoms were not static, predictable structures, they were living patterns of energy, governed by mathematics yet full of mystery. Schrödinger's insight reshaped the very way scientists thought about matter and energy, transforming quantum theory from a set of strange rules into a living, comprehensible framework. Despite these revolutionary achievements, Schrödinger remained modest. He often emphasized that his equation was a tool, not the ultimate answer. He believed that science should be approached with humility, that every discovery revealed both knowledge and its limits. The wave equation allowed humanity to describe the quantum world with precision, but it did not provide a final explanation of why the universe behaved as it did. This sense of wonder, the recognition that even profound insights are only part of a greater mystery, defined Schrödinger's approach to physics throughout his life. Schrödinger's work also highlighted the deep connection between mathematics and physical reality. The structure of the wave equation, its differential operators, its relationship to energy, its ability to describe probability waves, suggested that the universe itself could be expressed mathematically. For Schrödinger, this was not mere coincidence. He believed that the patterns of nature were encoded in the language of mathematics, waiting to be discovered by those who approached the world with curiosity, patience, and imagination. In this sense, the wave equation was not just a scientific breakthrough, it was a testament to the power of human thought. Throughout the late 1920s and early 1930s, Schrödinger's equation became a central focus of research. Physicists applied it to atoms beyond hydrogen, exploring more complex systems and revealing the subtle interplay of forces within matter. Each new application confirmed the robustness of Schrödinger's vision. The wave equation did not just predict outcomes, it offered a conceptual framework for understanding why those outcomes occurred. It brought elegance to chaos, continuity to fragmentation, and clarity to mystery. At the same time, the equation inspired new debates about the nature of reality. If particles were waves, how did they appear as localized objects when measured? Could a mathematical function truly represent physical existence? Or was it merely a tool for prediction? Schrödinger wrestled with these questions throughout his life, never fully satisfied with the prevailing interpretations. In his famous thought experiments, such as the cat paradox, he dramatized the tension between the mathematical description and our everyday experience of reality. These reflections revealed that his wave mechanics was not only a technical achievement, but a philosophical challenge, a way of asking humanity to reconsider what it means to know, to observe, and to exist. Beyond its theoretical and philosophical significance, the wave equation had practical consequences that would resonate for generations. It became the foundation for quantum chemistry, allowing scientists to predict molecular bonds, reaction rates, and the structure of complex materials. It provided the basis for semiconductor physics, which underpins modern electronics. It guided the development of nuclear models, helping humanity understand the forces that govern stars and atomic nuclei. In short, Schrödinger's mathematical insight became the engine for technological and scientific progress, influencing fields far beyond his original vision. Yet perhaps the most remarkable aspect of Schrödinger's achievement was how it reconciled logic and imagination. The wave equation demanded rigorous calculation, but it also required intuitive understanding. Scientists could not merely apply the mathematics mechanically, they had to visualize the behavior of waves, to feel their oscillations, to sense the harmony of energy and matter. Schrödinger had created a tool that was both precise and poetic, technical and philosophical, a rare accomplishment in the history of science. His wave equation also exemplified the power of persistence and solitary reflection. Schrödinger's breakthroughs were not the result of chance or competition, but of years of dedicated thought, observation, and contemplation. He combined classical knowledge with daring innovation, mathematics with intuition, analysis with imagination. This holistic approach allowed him to see connections others overlooked, to transform abstract ideas into concrete predictions, and to reveal the hidden architecture of the universe. Even as he aged, Schrödinger remained a thinker who sought to unify knowledge across disciplines. He applied his wave mechanics not only to physics but to biology, philosophy, and the study of consciousness. He saw patterns everywhere, believing that the laws governing electrons could illuminate the processes of life and thought. The wave equation, in his view, was more than a tool, it was a window into the fundamental principles of existence itself. In the story of quantum theory, Schrödinger's wave equation stands as a turning point, a moment when the abstract and the tangible, the mathematical and the philosophical, were woven into a single coherent vision. It transformed not only the practice of physics, but also the imagination of scientists and thinkers across generations. Every application, from the behavior of atoms to the design of modern technology, traces back to the elegant formulation that Schrödinger developed in his quiet, thoughtful study. Ultimately, The wave equation illustrates the power of combining insight with discipline, imagination with precision. Schrödinger did not merely solve a mathematical problem, he reshaped our understanding of reality. He showed that the quantum world, though strange and counterintuitive, could be described with elegance, continuity, and harmony. He gave humanity a new lens through which to view the universe, one that revealed both its subtle beauty and its profound mystery. In reflecting on the impact of Schrödinger's wave mechanics, one cannot overstate its significance. It transformed quantum theory, it unified disparate observations, and it provided the foundation for countless scientific advances. More than that, it transformed the way humans think about the world not as a series of disconnected events, but as an interconnected wave-like system, alive with patterns and potential. It is a vision that continues to inspire curiosity, creativity, and philosophical reflection, a lasting legacy of a thinker who dared to see the universe in a new way. In the annals of 20th century science, few intellectual confrontations have had the resonance and drama of the debates surrounding quantum mechanics. It was a time when physics was no longer simply a technical pursuit, it had become a philosophical battleground. The rules that governed the atomic and subatomic world challenged the very notions of reality, causality, and observation. At the center of this storm was Erwin Schrödinger, the quiet, contemplative Austrian physicist, whose wave mechanics had transformed the quantum landscape. But Schrödinger's contributions extended beyond equations and predictions. He brought a deep philosophical sensibility to the debate, questioning not just how the universe behaved, but what it meant for something to exist at all. Among Schrödinger's contemporaries, few were more iconic than Albert Einstein and Niels Bohr. Einstein, revered for his theory of relativity, was a scientist whose genius lay not only in calculation but in his relentless pursuit of conceptual clarity. He could imagine the curvature of space, time, and the bending of light around stars, yet he remained deeply skeptical of the emerging quantum theory. To Einstein, quantum mechanics was incomplete, an elegant formalism, yes, but one that left too much to chance. Schrödinger, in his own way, shared a similar discomfort. While he had developed the wave equation that provided predictive power, he was uneasy with the notion that the universe was fundamentally probabilistic. His debate with Bohr, therefore, was not simply an argument over mathematics, it was a profound exploration of the philosophical foundations of reality. Schrödinger's engagement with these intellectual giants began in the mid-1920s, shortly after he had formulated his wave mechanics. His equation offered a continuous, deterministic view of atomic behavior, a sharp contrast to Heisenberg's matrix mechanics and the Copenhagen interpretation, which emphasized uncertainty and probability. Schrödinger felt compelled to question the prevailing view. For him, the quantum world should not be governed by randomness, it should possess an underlying order, a wave-like harmony that mathematics could capture. Yet the Copenhagen interpretation, championed by Bohr, suggested that nature itself was probabilistic, that the outcome of a measurement could not be determined until the act of observation occurred. To Schrödinger, this was more than a scientific disagreement, it was a challenge to reason itself. In private letters and public lectures, Schrödinger articulated his objections. He argued that the Copenhagen view blurred the line between the observer and the observed. If a particle's state only became definite when measured, did reality itself depend on human consciousness? Schrödinger found this idea unsettling. Science, he believed, should describe reality as it exists independently of our observation. This philosophical stance led him to create one of the most famous thought experiments in history. The scenario of a cat placed in a sealed box with a radioactive atom, a poison vial, and a mechanism that could kill the cat depending on the atom's decay. The point was not to terrorize felines, but to illustrate the paradox of applying quantum rules to macroscopic objects. Could the cat be simultaneously alive and dead, in a superposition of states, until someone opened the box? Schrödinger used this vivid example to dramatize the conceptual tension between mathematics and observable reality. The cat paradox became an intellectual lightning rod. Einstein, who shared Schrödinger's unease with the probabilistic interpretation, famously remarked, "God does not play dice with the universe." The statement, both poetic and forceful, captured the essence of their skepticism. To Einstein and Schrödinger alike, the mathematics of quantum mechanics was undeniable in its predictive accuracy, yet it seemed to sidestep the deeper question of what was actually happening in nature. Did the electron have a defined position and momentum at all times, or was reality fundamentally indeterminate? This was the question that animated countless letters, lectures, and debates across Europe. Schrödinger's interactions with Bohr, in particular, were both intense and illuminating. Bohr, a Danish physicist of extraordinary intellect, embraced the probabilistic interpretation and defended it with eloquence. He argued that the quantum world defied classical intuition and that physicists must accept the limitations of observation. Reality, he suggested, could not be understood independently of measurement. Schrödinger listened carefully, acknowledging the elegance of Bohr's argument, yet he could not reconcile it with his sense of continuity and harmony. Their debates were not acrimonious but profoundly serious, as each thinker sought to probe the philosophical underpinnings of the equations they both respected. The intensity of these discussions reflected the broader struggle of physics to understand a world that had become increasingly counterintuitive. Schrödinger, Einstein, and Bohr were grappling not only with equations, but with fundamental questions about existence. What did it mean for a particle to exist? Could the act of observation alter reality itself? Was the universe inherently random, or did it follow hidden deterministic laws? Schrödinger's thoughtfulness added a crucial dimension to these debates. He did not merely challenge Copenhagen orthodoxy, he invited his peers to consider the conceptual meaning behind their mathematics. While his wave equation provided a deterministic framework, Schrödinger recognized that human intuition often failed in the quantum domain. The mathematics described behavior that contradicted everyday experience. Waves behaving like particles, particles existing in multiple states at once. He sought a philosophical language to bridge this gap. His writings reveal a mind striving to reconcile the abstract precision of mathematics with the tangible reality of the physical world. He insisted that science should aim not only to predict outcomes, but to deepen understanding of the universe's nature. These debates were not confined to academic journals. Schrödinger and his colleagues engaged in correspondence, personal meetings, and conferences, shaping the dialogue of the era. The Solvay conferences in the late 1920s became legendary arenas for these discussions. Schrödinger's calm, reflective demeanor contrasted with the fiery intensity of some participants. He often used analogies drawn from music, literature, and philosophy to clarify his points, demonstrating that understanding quantum reality required more than calculation. It required imagination and insight. The philosophical depth of Schrödinger's engagement was evident in his critique of measurement. He asked, "If an electron's position is only definite when measured, what does this imply about reality before measurement? Could a system exist in a superposition of states? And if so, how could these microscopic rules scale to the macroscopic world we inhabit?" His cat paradox dramatized these questions with simplicity and clarity. It revealed the tension between mathematical abstraction and physical intuition, and it forced the scientific community to confront the limits of their understanding. Einstein, for his part, shared Schrödinger's concern that quantum mechanics was incomplete. He envisioned a hidden variables theory that would restore determinism to the atomic world. Schrödinger explored similar ideas, wondering whether the wave function might correspond to a physically real field rather than a mere probability amplitude. Their mutual dissatisfaction with Copenhagen orthodoxy created a rare intellectual kinship, a shared determination to probe the philosophical foundations of their science. Even at the risk of professional disagreement, Bohr, however, remained a formidable interlocutor. He insisted that the nature of quantum reality could not be separated from the conditions of observation. In his view, attempting to impose classical determinism on a fundamentally quantum system was misguided. Schrödinger listened, reflected, and countered, emphasizing that science should aim for a coherent picture of reality, not merely a predictive tool. Their exchanges were nuanced, requiring careful attention to both logic and metaphor. These dialogues illuminated the philosophical richness of quantum mechanics, transforming debates about mathematics into debates about existence itself. Throughout these exchanges, Schrödinger's own thinking evolved. He began to appreciate the subtleties of Bohr's perspective, recognizing that quantum theory challenged deeply held assumptions about space, time, and causality, yet he never abandoned his insistence on continuity and determinism. His reflections led him to explore connections between physics and philosophy, particularly the nature of consciousness and observation. He wondered whether understanding quantum mechanics required insights not only from mathematics, but from the study of perception, cognition, and even metaphysics. The impact of these debates extended far beyond Schrödinger's lifetime. The questions he raised about the role of observation, the nature of superposition, and the meaning of reality continued to inspire research and discussion in quantum foundations, philosophy of science, and even emerging fields such as quantum computing. His thought experiments, once regarded as playful hypotheticals, are now central to experiments that probe entanglement, decoherence, and the limits of measurement. In this way, Schrödinger's philosophical engagement shaped the trajectory of science as profoundly as his equations. At the heart of these discussions was Schrödinger's belief that scientific inquiry must be intellectually honest and conceptually coherent. He resisted the temptation to accept formalism without understanding. For him, equations were not enough. They had to correspond to a comprehensible reality. This insistence on philosophical depth set him apart from many of his contemporaries. He did not seek to dominate debates with authority or rhetoric. He sought clarity, coherence, and insight. His debates with Einstein and Bohr were not contests of ego but explorations of meaning, demonstrating that physics and philosophy are inseparable when confronting the quantum world. These exchanges also reveal Schrödinger's remarkable ability to communicate complex ideas with clarity. He often used vivid analogies, drawing from literature, art, and daily experience to make abstract concepts accessible. The cat paradox is a prime example. It distilled a profound philosophical issue into a simple, memorable narrative. By doing so, Schrödinger ensured that the debate over quantum reality was not confined to specialists. It became part of the broader intellectual discourse, influencing generations of thinkers, scientists, and students. Even as he challenged prevailing interpretations, Schrödinger remained a meticulous scientist. His critiques were grounded in rigorous analysis, careful reasoning, and an intimate understanding of the mathematics. He demonstrated that philosophical reflection and scientific precision are not mutually exclusive. Indeed, his insistence on conceptual clarity strengthened the development of quantum mechanics, prompting his peers to refine their interpretations and explore deeper questions about measurement, probability, and the ontology of quantum systems. Schrödinger's debates with Einstein and Bohr also highlighted the human dimension of scientific discovery. These were not abstract arguments conducted in isolation, they were dialogues between individuals, shaped by personality, intuition, and values. Einstein's moral and aesthetic sense of determinism, Bohr's philosophical pragmatism, and Schrödinger's poetic sense of harmony created a rich tapestry of ideas. The debates exemplify how science is both a technical enterprise and a profoundly human activity, where imagination, intuition, and ethical reflection interact with calculation and observation. In reflecting on these debates, it becomes clear that Schrödinger's contributions were as philosophical as they were scientific. He transformed quantum mechanics from a set of equations into a medium for exploring fundamental questions about reality. He insisted that understanding the universe required more than computation, it required contemplation, imagination, and philosophical rigor. His dialogues with Einstein and Bohr illuminate the depth of these concerns, showing that science, at its highest level, is inseparable from the search for meaning. As Schrödinger continued his exchanges with Bohr and Einstein, the philosophical stakes of quantum mechanics became ever clearer. It was no longer simply a question of predicting experimental outcomes. It was a matter of understanding what it meant for something to exist. Schrödinger repeatedly emphasized that a scientific theory should describe reality as it is, not merely as it appears to an observer. The Copenhagen interpretation, with its insistence on probabilities and observer-dependent states, represented for him a retreat from the quest for understanding. Schrödinger's insistence on a coherent, continuous reality challenged his contemporaries to reconsider the very nature of explanation in science. His cat thought experiment became the most vivid symbol of this challenge. It was deliberately paradoxical, a cat both alive and dead, existing in a superposition of states until observed. The absurdity was intentional, designed to expose the tension between microscopic quantum phenomena and macroscopic reality. Schrödinger's point was not to suggest that cats are literally suspended in existential limbo, but to question the notion that human observation creates reality. How could the laws of physics allow a system to be simultaneously in mutually exclusive states? And if this were true for particles, what did it imply for the nature of the world we experience? These questions struck at the heart of quantum mechanics and revealed the profound philosophical implications of Schrödinger's work. Einstein shared Schrödinger's discomfort. Though he had helped to lay the foundations of modern physics, he had a deep aversion to the idea that the universe was governed by randomness. For both men, science was a search for underlying order, a coherent description of how reality operates independently of human perception. Schrödinger and Einstein often corresponded and met in person to discuss these issues, probing the limitations of the Copenhagen interpretation. Einstein's famous objection that God does not play dice with the universe resonated with Schrödinger's own convictions, reinforcing the idea that the probabilistic framework, while mathematically powerful, might be conceptually incomplete. Bohr, however, was unwavering in his defense of the Copenhagen interpretation. He argued that quantum mechanics was not meant to describe reality in classical terms, but rather to provide a framework for predicting experimental outcomes. The act of measurement, he insisted, is fundamental. The observer and the observed cannot be separated. Schrödinger understood the logic, yet he could not reconcile it with his vision of a unified, deterministic universe. Their debates were intense, often conducted in front of peers at conferences or in carefully crafted publications. They explored the philosophical consequences of superposition, entanglement, and complementarity, forcing the scientific community to confront questions that transcended mere computation. These exchanges highlighted Schrödinger's unique position as both a physicist and a philosopher. Unlike some contemporaries, he approached quantum mechanics not solely as a mathematical formalism, but as a reflection of reality itself. He insisted on conceptual clarity, asking what equations actually represented and what they implied about the nature of existence. His thought experiments and writings conveyed this dual focus, rigorous scientific analysis combined with philosophical depth. Schrödinger's insistence on this approach influenced the development of quantum foundations, inspiring future generations to examine not only how particles behave, but what it means for them to exist. The philosophical depth of Schrödinger's debates extended to questions of determinism, causality, and the role of consciousness. If the wave function represents reality, does it evolve deterministically according to the Schrödinger equation, or is its collapse upon measurement a fundamental feature of nature? Could human observation influence the course of events at the atomic level? Schrödinger grappled with these questions throughout his career, recognizing that they touch upon the limits of knowledge and the interplay between mind and matter. In doing so, he positioned himself at the intersection of physics, metaphysics, and epistemology. Moreover, Schrödinger's dialogues with Einstein and Bohr had practical implications for the interpretation of experiments. His thought experiments challenged scientists to design experiments that could probe the boundaries of quantum mechanics, leading to new investigations into entanglement, decoherence, and the measurement problem. By questioning assumptions and highlighting paradoxes, Schrödinger's philosophical perspective stimulated the scientific community to test the foundations of their theories, reinforcing the dynamic interplay between conceptual reflection and empirical investigation. In addition to formal debates, Schrödinger engaged in extensive correspondence with other leading physicists. These letters reveal a mind deeply concerned with both technical detail and philosophical meaning. He often explained complex mathematical ideas using vivid metaphors, such as waves in a pond or vibrations in a musical instrument, emphasizing the need to connect abstract formalism with intuitive understanding. His clarity and elegance of thought made his ideas accessible and influential, extending the reach of his philosophical insights beyond the circle of immediate collaborators. Schrödinger's engagement with Einstein was particularly illuminating. Einstein, although skeptical of the probabilistic interpretation, shared Schrödinger's desire for a coherent description of reality. Together, they explored the possibility of hidden variables, unknown parameters that could restore determinism to quantum mechanics. While the hidden variable approach would later be formalized by David Bohm, the seeds of this idea can be traced to the philosophical challenges that Schrödinger and Einstein articulated. Their collaboration highlights how deep conceptual questioning can drive the evolution of scientific theory, even when immediate solutions remain elusive. The debates also illuminated the human dimension of scientific inquiry. Schrödinger, Einstein, and Bohr were not merely debating equations, they were negotiating deeply held beliefs about the nature of reality, the limits of knowledge, and the role of the observer. Their interactions demonstrate that science is both an intellectual and a human enterprise, shaped by curiosity, intuition, and philosophical reflection as much as by experiment and computation. Schrödinger's contributions exemplify this dual aspect, showing how a scientist can simultaneously engage with rigorous mathematics and profound existential questions. Schrödinger's cat paradox, in particular, became a lasting symbol of these philosophical challenges. It crystallized the tension between the microscopic rules of quantum mechanics and the macroscopic world of everyday experience. The paradox forced physicists to confront uncomfortable questions: can a system exist in multiple states simultaneously? Does measurement create reality, or merely reveal it? What is the nature of superposition and entanglement? Schrödinger's elegant framing of these questions continues to shape contemporary research in quantum foundations, demonstrating the enduring value of philosophical reflection in science. The influence of Schrödinger's debates extended beyond physics into philosophy and cognitive science. His insistence on the relationship between observation, consciousness, and reality inspired later thinkers to explore the intersection of mind and matter. Questions raised during these debates, such as the role of the observer in defining reality, continue to resonate in discussions of quantum consciousness, information theory, and the philosophy of perception. Schrödinger's legacy, therefore, is not confined to equations or laboratory experiments. It encompasses a broader intellectual vision that continues to challenge and inspire. Even as quantum mechanics became more widely accepted, Schrödinger remained committed to questioning its foundational assumptions. He recognized that the predictive success of the theory did not resolve the deeper questions about the ontology of the wave function. His insistence on conceptual clarity encouraged scientists to differentiate between mathematical formalism and physical reality, fostering a more nuanced understanding of what quantum mechanics could and could not tell us about the universe. In this sense, Schrödinger's philosophical engagement functioned as a critical corrective, ensuring that science remained reflective, as well as empirical. Throughout these debates, Schrödinger maintained a remarkable balance of rigor and imagination. He could engage with complex equations, explore subtle logical implications, and simultaneously consider metaphorical and philosophical interpretations. This ability allowed him to communicate profound ideas in accessible ways, making abstract issues concrete without oversimplifying. His dialogues with Bohr and Einstein were thus not only intellectually productive, but also pedagogically valuable, demonstrating how philosophical questioning can enrich scientific understanding. The impact of Schrödinger's debates is evident in the ongoing research they inspired. Experiments designed to test superposition, entanglement, and the measurement problem directly trace their conceptual roots to the issues he raised. The development of quantum information theory, quantum cryptography, and experimental tests of Bell's inequalities all owe a debt to the philosophical rigor that Schrödinger introduced. By insisting that equations must correspond to reality and by dramatizing the conceptual challenges of quantum mechanics, he shaped the very questions that continue to guide research in the field. Schrödinger's engagement with Einstein and Bohr also highlights the interplay between individual insight and collaborative discourse in science. Breakthroughs rarely occur in isolation, they emerge from dialogue, critique, and reflection. Schrödinger's willingness to challenge prevailing interpretations, to articulate paradoxes, and to explore philosophical consequences exemplifies how intellectual courage and curiosity can drive scientific progress. The debates demonstrate that science is not merely a collection of facts, but a conversation about meaning, coherence, and understanding. Moreover, Schrödinger's approach exemplifies the importance of integrating multiple perspectives. He drew on mathematics, physics, philosophy, and even literary imagination to explore the implications of quantum mechanics. This interdisciplinary sensibility allowed him to pose questions that others might overlook, bridging gaps between formalism and intuition. It also reinforced the idea that scientific understanding is enriched when diverse ways of thinking, logical, conceptual, and creative, are brought to bear on complex problems. The philosophical depth revealed in these debates continues to resonate in contemporary discussions of quantum mechanics. Modern experiments probing quantum superposition, entanglement, and the role of observation directly address the issues Schrödinger highlighted. The questions he raised about the relationship between measurement and reality remain central to quantum foundations. In this sense, his debates with Einstein and Bohr are not historical curiosities, they are active, living discussions that continue to shape the way we think about the quantum world. Even decades later, Schrödinger's thought experiments remain pedagogical touchstones. They illustrate the tension between formalism and intuition, highlighting the importance of conceptual clarity in science. They encourage students and researchers to ask not only whether a theory works, but why it works and what it implies about reality. In doing so, Schrödinger's philosophical engagement continues to guide generations of thinkers, reinforcing the principle that scientific rigor and philosophical reflection are mutually. Erwin Schrödinger was not only a physicist, but also a thinker who sought to explore the deeper implications of science for understanding life itself. While he had already transformed quantum mechanics with his wave equation, his curiosity extended far beyond the microscopic world of atoms and electrons. He was fascinated by the question of what distinguishes living systems from inanimate matter. This question, which had occupied philosophers for centuries, now became the focus of Schrödinger's inquiry. He approached it with the same rigor and imagination that had guided his work in physics, combining mathematics, logic, and philosophical reflection to explore the fundamental nature of life. In the late 1940s, Schrödinger turned his attention to biology, recognizing that the principles of physics must underpin the behavior of living systems. He asked how organisms maintain order and stability in the face of the disorder and chaos that the second law of thermodynamics predicts. Living beings seem to defy entropy, sustaining structure and function over time. Schrödinger realized that this mystery could be approached scientifically. Life, he proposed, could be understood as an extraordinary physical phenomenon in which information plays a central role. He coined the concept of a periodic crystal to describe the molecular basis of genetic information, suggesting that hereditary material must be stable yet capable of encoding complexity. This idea, presented in his influential book What is Life, resonated profoundly with the scientific community. Schrödinger argued that the physical laws governing molecules could explain biological phenomena, linking quantum mechanics, thermodynamics, and genetics in a way that had never been done before. He envisioned DNA and other genetic molecules as carriers of information, structured in patterns that determine the characteristics of living organisms. This was revolutionary because it framed life in terms of physics, chemistry, and mathematics, rather than relying solely on descriptive biology. Schrödinger's insights inspired a generation of scientists, including many of the pioneers of molecular biology. His ideas provided conceptual scaffolding for the discovery of the double helix structure of DNA and the understanding of how genetic information is stored and transmitted. He suggested that life could be studied as a problem in physics, that organisms obey the same laws as all other matter, but in ways that produce remarkable order and complexity. By applying quantum principles and thermodynamic reasoning, Schrödinger demonstrated that the stability of genetic material, the transmission of hereditary traits, and the processes of metabolism could all be explored through scientific methods. In addition to biology, Schrödinger's reflections extended into philosophy. He was deeply interested in questions of consciousness, perception, and the relationship between mind and matter. He recognized that quantum mechanics not only challenged classical notions of reality, but also raised profound questions about observation and awareness. If measurement plays a fundamental role in determining the state of a system, what does this imply about the observer? Schrödinger speculated that consciousness could not be entirely separated from the physical processes it observes, hinting at connections between the physical and experiential worlds that remain topics of philosophical inquiry today. His interdisciplinary approach was remarkable for its time. Schrödinger moved fluidly between the domains of physics, biology, and philosophy, seeking to unify knowledge rather than compartmentalize it. He believed that understanding life required not only empirical observation, but also conceptual clarity, the ability to see underlying patterns and principles that connect seemingly disparate phenomena. This holistic perspective set him apart from many contemporaries, positioning him as a thinker whose influence extended well beyond the confines of a single scientific discipline. Schrödinger's ideas also challenged conventional views of determinism. While classical physics had often been interpreted as rigidly deterministic, his work suggested that life operates at the intersection of order and probability. Biological systems exhibit remarkable regularity, yet they are also shaped by stochastic processes at the molecular level. By applying quantum concepts to biology, Schrödinger illuminated the delicate balance between predictability and chance that characterizes living systems. This insight provided a new lens through which to understand evolution, mutation, and the adaptability of organisms, highlighting the subtle interplay of law and randomness in the natural world. Moreover, Schrödinger's reflections on life emphasized the importance of information as a fundamental concept. He suggested that the stability of hereditary material and the processes that sustain life could be understood as the storage, transmission, and interpretation of information. This anticipation of what would later become the field of molecular information theory demonstrated Schrödinger's ability to think far ahead of his time, bridging physics and biology in ways that continue to resonate in contemporary science. Beyond scientific theory, Schrödinger's interdisciplinary work had philosophical and cultural significance. He challenged the notion that science and philosophy are separate enterprises, demonstrating that profound questions about life, consciousness, and reality require both empirical rigor and conceptual exploration. By framing biology as a problem in physics, he provided a language for understanding the living world that was quantitative, logical, and deeply reflective. His work encouraged scientists to consider not only how life functions, but why it exhibits the remarkable properties it does, fostering a sense of wonder and intellectual curiosity that extended beyond laboratory walls. Schrödinger's influence in biology also reflected his belief in the universality of scientific principles. He argued that the same physical laws govern all phenomena, from the smallest particles to the complexity of living organisms. This perspective helped bridge disciplinary divides, encouraging collaboration between physicists, chemists, and biologists. His vision of a unified approach to understanding nature anticipated modern systems biology, molecular genetics, and computational modeling of life processes, demonstrating the enduring relevance of his interdisciplinary thinking. At the heart of Schrödinger's contributions to biology and philosophy was a search for coherence. He sought to identify the principles that make life possible, to understand how order emerges from chaos, and to explore the connections between matter, energy, and information. His reflections were guided by both scientific rigor and aesthetic sensibility, revealing a mind attuned to both precision and beauty. This combination allowed him to pose questions and propose ideas that were not only technically innovative, but also conceptually profound. Even today, Schrödinger's work continues to inspire inquiry at the intersection of physics, biology, and philosophy. His notion of an aperiodic crystal foreshadowed molecular biology, while his reflections on information and life resonate in contemporary studies of genetics and systems biology. His philosophical insights continue to inform discussions of consciousness, the measurement problem, and the interpretation of quantum mechanics. Schrödinger's approach demonstrates that the quest to understand life is not confined to one discipline, but requires a synthesis of knowledge, imagination, and reflection. In summary, Schrödinger's exploration of life extended the reach of his scientific genius beyond quantum mechanics. He applied physical principles to biological questions, introduced the concept of informational stability in genetics, and challenged traditional boundaries between disciplines. His work illuminated the delicate balance of order and randomness in living systems, provided a conceptual foundation for molecular biology, and inspired philosophical reflection on the nature of consciousness and reality. By bridging physics, biology, and philosophy, Schrödinger demonstrated that the search to understand life is both scientific and deeply human, revealing the interconnectedness of knowledge, observation, and meaning. Erwin Schrödinger's legacy in physics extends far beyond the equations he formulated. It is perhaps most vividly reflected in his ability to frame the deepest questions of reality in ways that challenge perception and understanding. Among his most enduring contributions are his thought experiments, conceptual devices designed not to provide answers, but to illuminate the paradoxes inherent in quantum mechanics. These experiments transformed the way physicists and philosophers approached the nature of existence, measurement, and the interface between observation and reality. They are remarkable not merely for their intellectual audacity, but for their enduring capacity to provoke debate and insight. Schrödinger's most famous thought experiment, commonly known as the cat paradox, captures the essence of the tension between quantum mechanics and everyday experience. By imagining a cat enclosed in a sealed box with a mechanism that depends on a quantum event, he dramatized the conflict between the mathematical description of subatomic particles and the observable, macroscopic world. The cat, according to the mathematical formalism, exists in a superposition of states, both alive and dead, until an observation is made. This vivid imagery made abstract quantum principles tangible, forcing scientists to confront the puzzling implications of superposition and measurement. It was not intended as a literal scenario, but as a conceptual lens, revealing the contradictions between classical intuition and quantum formalism. The power of this thought experiment lies in its capacity to highlight a fundamental question: What does it mean for a system to exist in a particular state? In classical physics, objects possess definite properties independent of observation. A ball is either here or there, a clock either ticks or it does not. Quantum mechanics, however, defies this intuition. Particles can exist in multiple states simultaneously, and the act of measurement appears to collapse these possibilities into a single outcome. Schrödinger's cat encapsulates this conceptual challenge, providing a bridge between rigorous mathematical theory and philosophical reflection. The paradox asks the observer to reconsider assumptions about reality, determinism, and the limits of knowledge. Beyond the cat experiment, Schrödinger devised other thought experiments and analogies to explore the nature of wave functions and superposition. He consistently sought to make the invisible visible, translating complex equations into scenarios that could be grasped intuitively. By framing quantum phenomena in terms of everyday objects and experiences, he emphasized that the strangeness of the quantum world is not an abstract curiosity, but a real challenge to understanding the nature of reality itself. These thought experiments served as intellectual tools, guiding physicists in thinking critically about the interpretations of quantum mechanics and the philosophical implications of their work. Schrödinger's experiments also had a profound influence on the philosophical interpretation of quantum mechanics. They raised questions about the meaning of probability, the role of the observer, and the distinction between the microscopic and macroscopic worlds. His paradoxes forced scientists to consider whether quantum mechanics describes reality as it is or merely predicts outcomes. This distinction continues to animate debates in physics today, influencing interpretations such as the many worlds theory, decoherence approaches, and objective collapse models. Schrödinger's conceptual clarity ensured that these discussions were grounded in the mathematical and physical realities of quantum mechanics, even as they explored philosophical terrain. One of the remarkable aspects of Schrödinger's thought experiments is their capacity to unify scientific rigor with imaginative exploration. He did not propose these experiments lightly. They were grounded in his deep understanding of the mathematics of wave functions and the principles of quantum theory. Yet, he also recognized that equations alone are insufficient to grasp the philosophical consequences of a theory. Thought experiments allowed him to extend reasoning beyond the laboratory, to test the coherence of principles, and to expose potential contradictions or counterintuitive outcomes. In this way, they became a form of intellectual experimentation, a complement to empirical investigation that probes the conceptual foundations of science. The implications of Schrödinger's thought experiments were not confined to philosophical reflection. They influenced the development of quantum theory itself. By highlighting paradoxes and conceptual gaps, these experiments encouraged physicists to refine their models, explore new interpretations, and devise experimental tests that probe the boundaries of measurement and superposition. In particular, Schrödinger's work inspired attention to the measurement problem, the question of how, why, and when quantum possibilities collapse into definite outcomes. This problem remains central to contemporary quantum research, guiding investigations into quantum computing, entanglement, and the fundamental nature of information. Schrödinger's intellectual approach also emphasized the continuity of science and philosophy. He demonstrated that scientific progress is not merely a matter of accumulating data or solving equations, but requires reflection on meaning, coherence, and conceptual foundations. His thought experiments exemplify this integration, showing that even highly technical theories can be enriched by imaginative and philosophical inquiry. By bridging the gap between abstract formalism and conceptual clarity, Schrödinger provided a model for thinking deeply about the implications of scientific knowledge, one that continues to inform contemporary discussions in physics and philosophy alike. Furthermore, the impact of Schrödinger's thought experiments extends into pedagogy and public understanding. The cat paradox, in particular, has become a cultural symbol, illustrating the strange logic of quantum mechanics to students, scholars, and the general public. Its appeal lies not merely in the scenario itself, but in its capacity to convey complex scientific principles in accessible and memorable terms. Schrödinger showed that conceptual clarity is as important as computational skill, that understanding a theory involves grappling with its philosophical consequences as much as applying its mathematical machinery. Schrödinger's influence also highlights the enduring importance of conceptual creativity in science. His ability to imagine paradoxical situations and explore their consequences exemplifies a form of intellectual courage. He was willing to challenge prevailing assumptions, to pose questions that had no immediate answer, and to provoke reflection on the foundations of knowledge. This approach demonstrates that scientific advancement is not only a technical endeavor, but also a deeply creative one, requiring insight, intuition, and the willingness to confront uncertainty. The thought experiments also underscore the interconnectedness of different domains of inquiry. Schrödinger drew upon physics, mathematics, philosophy, and even elements of everyday experience to construct scenarios that illuminate deep truths about the universe. By doing so, he modeled an integrative approach to understanding reality, one that recognizes the limits of narrow specialization and the value of cross-disciplinary thinking. His work reminds us that profound insights often emerge at the intersections of fields, where different perspectives converge to reveal hidden structures and patterns. In reflecting on the legacy of Schrödinger's thought experiments, it becomes clear that their significance lies not only in the specific paradoxes he posed, but in the mode of thinking they exemplify. They encourage careful reasoning, imaginative exploration, and philosophical reflection, all grounded in scientific knowledge. They challenge assumptions, expose contradictions, and invite ongoing inquiry. In doing so, they have reshaped the understanding of reality itself, emphasizing the subtle, counterintuitive, and profoundly interconnected nature of the quantum world. Ultimately, Schrödinger's experiments remind us that science is as much about questions as answers. They highlight the limits of intuition, the challenges of interpreting mathematical formalism, and the need to engage with the conceptual foundations of knowledge. By dramatizing the paradoxes inherent in quantum mechanics, Schrödinger provided a lens through which the scientific community and the broader public could confront the strangeness of reality, encouraging curiosity, critical thinking, and philosophical reflection. In this sense, Schrödinger's thought experiments remain timeless. They are not relics of a bygone era, but living tools that continue to shape research, teaching, and public understanding. They exemplify the power of imagination grounded in scientific knowledge, demonstrating how conceptual creativity can illuminate truths that elude direct measurement. Through these experiments, Schrödinger reshaped not only physics but the way humans think about existence, observation, and the nature of reality itself. Erwin Schrödinger's contributions to quantum theory were not limited to abstract equations or philosophical reflection. They provided a practical and conceptual framework that continues to shape science and technology to this day. His formulation of wave mechanics offered a new way to describe the behavior of particles at the atomic and subatomic levels. Before Schrödinger, the emerging field of quantum mechanics was dominated by Heisenberg's matrix mechanics, which, though mathematically rigorous, was abstract and less intuitive. Schrödinger introduced an approach that combined mathematical precision with conceptual clarity, allowing scientists to visualize particles as wave-like entities and providing tools for predicting atomic behavior with remarkable accuracy. The wave equation he developed, now famously known as the Schrödinger equation, became the cornerstone of quantum mechanics. It describes how the quantum state of a physical system evolves over time, providing insight into the probabilities of finding a particle in a particular state or location. This formulation transformed theoretical physics, making it possible to calculate energy levels of atoms, the structure of molecules, and the behavior of electrons in chemical bonds. Schrödinger's approach bridged the gap between abstract mathematics and observable phenomena, offering both a predictive framework and a conceptual model that could be visualized and applied across multiple domains of science. The significance of Schrödinger's work is perhaps most evident in its impact on chemistry and molecular biology. By enabling precise calculations of electron behavior in atoms and molecules, his equations provided the foundation for understanding chemical reactions at a fundamental level. Quantum mechanics, grounded in Schrödinger's wave mechanics, allowed scientists to predict molecular structures, reaction rates, and bonding patterns with unprecedented accuracy. This capability revolutionized chemistry, transforming it from a largely empirical discipline into one deeply rooted in theory. Schrödinger's influence extended even further when his ideas inspired biologists to consider the molecular basis of life. Concepts such as the stability of genetic material and the informational structure of DNA can be traced back to the insights enabled by quantum theory, illustrating the profound interdisciplinary reach of his work. Beyond its theoretical importance, Schrödinger's framework has had tangible technological impacts. Modern electronics, semiconductors, lasers, and superconductors all rely on principles derived from quantum mechanics. Schrödinger's equations underpin the understanding of electron behavior in materials, guiding the design of devices that have transformed society. Quantum theory also forms the foundation for emerging technologies such as quantum computing, quantum cryptography, and advanced imaging techniques. In each of these fields, Schrödinger's vision that the quantum world can be described with clarity and precision continues to guide research, design, and innovation. Schrödinger's contributions also shaped scientific thought more broadly, influencing how researchers conceptualize the relationship between theory and reality. His wave mechanics offered an intuitive picture of quantum systems, complementing the probabilistic interpretation of the Copenhagen school. By framing particles as wave functions that evolve deterministically, Schrödinger emphasized continuity and coherence, providing an alternative lens through which to interpret quantum phenomena. This approach encouraged scientists to think critically about the philosophical and conceptual foundations of their work, highlighting the interplay between mathematics, observation, and interpretation. Another important dimension of Schrödinger's legacy lies in education and scientific communication. His approach to quantum mechanics, combining rigorous mathematics with conceptual clarity, made the subject accessible to students and researchers alike. His books, lectures, and publications provided explanations that illuminated the counterintuitive aspects of quantum theory, making it possible for generations of scientists to grasp the principles and apply them to new problems. By providing both the tools and the conceptual framework, Schrödinger ensured that quantum mechanics would not remain an esoteric specialty, but would become a central part of the broader scientific enterprise. Schrödinger's influence extends into the ongoing philosophical debates about quantum theory. The questions he raised about determinism, superposition, and the interpretation of the wave function continue to inform discussions on the nature of reality and measurement. Modern explorations of quantum information theory, entanglement, and the foundations of quantum mechanics all trace their intellectual lineage to the conceptual challenges Schrödinger highlighted. By linking rigorous mathematics with philosophical reflection, he encouraged scientists to consider not just how the universe behaves, but what it means for something to exist and be observed. The practical applications of Schrödinger's work are mirrored in the development of spectroscopy, atomic clocks, and quantum sensors. Wave mechanics allows precise predictions of energy transitions in atoms, which underpin technologies that define modern life, from GPS systems to medical imaging. These applications demonstrate the remarkable trajectory from abstract equations to devices that shape everyday experience, highlighting the enduring relevance of Schrödinger's insights. In addition to these technical achievements, Schrödinger's legacy reflects the broader intellectual culture of 20th century physics. He exemplified a rare combination of mathematical skill, conceptual imagination, and philosophical sensitivity. His ability to pose profound questions, develop elegant theoretical tools, and communicate complex ideas with clarity set a standard for scientific excellence. Schrödinger's work encouraged collaboration across disciplines, bridging physics, chemistry, biology, and philosophy, and illustrating the power of integrative thinking in advancing knowledge. The global impact of Schrödinger's contributions is evident in both research and pedagogy. Universities, research institutions, and laboratories around the world continue to teach and apply the principles he helped establish. His work forms the foundation for courses in quantum mechanics, molecular physics, and computational chemistry, shaping the education of countless scientists. The methodologies he developed are employed in laboratories from Tokyo to Cambridge, from MIT to CERN, demonstrating the universal applicability and enduring significance of his insights. Finally, Schrödinger's vision reminds us of the interplay between abstract theory and practical consequence. He demonstrated that fundamental understanding of the universe, grounded in rigorous mathematics and conceptual reflection, can lead to discoveries that transform technology, medicine, and society. His wave mechanics not only resolved pressing theoretical questions of his time, but also provided a foundation upon which generations of scientists could build, explore, and innovate. By bridging the realms of thought and application, Schrödinger exemplified the transformative potential of deep intellectual inquiry. In sum, Schrödinger's work laid the foundation for modern quantum theory, influencing both scientific thought and technological development for generations. His wave mechanics provided a predictive framework for atomic and molecular behavior, enabled breakthroughs in chemistry and biology, guided the development of modern technology, and shaped philosophical and educational discourse. His legacy demonstrates the profound impact of combining mathematical rigor, conceptual clarity, and philosophical insight, ensuring that the exploration of the quantum world continues to inspire, challenge, and transform human understanding. Erwin Schrödinger's life and work left an indelible mark on science, philosophy, and the way humanity understands the universe. Long after his equations and thought experiments were first introduced, his ideas continue to shape research, inspire inquiry, and challenge assumptions about the fundamental nature of reality. Schrödinger was not content to produce mathematical formulas alone. He sought a deeper understanding of what it means for something to exist, to be observed, and to interact with the physical world. His vision transcended the confines of physics, reaching into biology, philosophy, and even the nature of consciousness itself, leaving a legacy that remains profoundly relevant in the 21st century. Central to Schrödinger's enduring influence is his role in expanding the scope of scientific imagination. He demonstrated that theoretical physics could not be isolated from conceptual reflection. By framing the quantum world in terms of waves and probabilities, and by posing thought experiments that brought abstract paradoxes into a comprehensible narrative, Schrödinger encouraged scientists to think not only about how particles behave, but also about what the behavior signifies. The famous cat paradox remains emblematic of this approach, illustrating the tension between mathematical formalism and observable reality, and inspiring generations of physicists, philosophers, and curious minds to question assumptions about determinism, measurement, and the nature of existence. Schrödinger's work has had a lasting impact on the philosophy of science. His insistence on coherence, clarity, and conceptual understanding challenged scientists to examine the foundations of their theories. He asked whether equations alone were sufficient to describe reality, or whether a deeper interpretation was necessary. This philosophical rigor influenced subsequent generations of thinkers, shaping debates about the interpretation of quantum mechanics that continue to this day. Questions about the role of the observer, the nature of superposition, and the meaning of probability in quantum theory trace their intellectual roots to Schrödinger's reflections, ensuring that his work remains central to ongoing discussions in physics and philosophy alike. Beyond physics, Schrödinger's interdisciplinary vision reshaped the way science engages with life. His exploration of the physical basis of heredity and the informational structure of genes, presented in What is Life, bridged physics and biology in unprecedented ways. He introduced concepts that helped frame the molecular understanding of life, inspiring scientists such as James Watson, Francis Crick, and Maurice Wilkins in their discovery of the structure of DNA. By showing that the principles of quantum mechanics could illuminate the mechanisms of life, Schrödinger created a framework for the emerging field of molecular biology, demonstrating the power of cross-disciplinary thinking and the enduring value of conceptual insight. Schrödinger's influence extends into modern technology as well. Quantum mechanics, grounded in his wave mechanics, underpins the operation of semiconductors, lasers, superconductors, and other devices that define contemporary life. Emerging technologies such as quantum computing, quantum cryptography, and advanced materials research continue to rely on the conceptual framework he helped establish. His insistence on both precision and interpretive clarity ensures that modern scientists are not only applying equations, but also thinking critically about what those equations mean in the context of real-world phenomena. In this way, Schrödinger's legacy bridges theory and application, linking abstract thought to practical innovation. The intellectual ethos Schrödinger cultivated, combining rigor, imagination, and philosophical reflection, continues to inspire scientific exploration. His approach encourages researchers to challenge assumptions, to probe the conceptual foundations of their work, and to remain attentive to the philosophical implications of scientific discoveries. In a time when technological advancement often outpaces conceptual understanding, Schrödinger's example serves as a reminder that inquiry into the meaning of reality is as important as technical competence. His legacy encourages scientists to maintain a reflective stance, to consider the why alongside the how, and to integrate imaginative thinking with empirical rigor. In education, Schrödinger's impact is equally profound. His work has become a cornerstone of teaching in physics, chemistry, and biology. The Schrödinger equation, wave mechanics, and his thought experiments are standard components of curricula worldwide, providing students with both the mathematical tools and the conceptual frameworks necessary to understand quantum mechanics. By emphasizing conceptual clarity alongside technical skill, Schrödinger's approach fosters deep comprehension and critical thinking, ensuring that each new generation of scientists engages meaningfully with the philosophical as well as the empirical dimensions of their field. Schrödinger's influence also extends into public imagination. The vivid imagery of his thought experiments, particularly the cat paradox, has permeated literature, art, and popular science, helping non-specialists engage with the strange and fascinating realities of quantum mechanics. By translating complex scientific ideas into memorable narratives, Schrödinger demonstrated that science could be both intellectually rigorous and accessible, encouraging curiosity, reflection, and dialogue across disciplines and audiences. His work serves as a bridge between the technical realm of physics and the broader human quest to understand the world. Philosophically, Schrödinger's legacy is intertwined with enduring questions about consciousness, observation, and reality. He recognized that quantum mechanics challenges classical assumptions, forcing humanity to reconsider notions of causality, determinism, and the relationship between mind and matter. His reflections anticipated contemporary debates on quantum information, the measurement problem, and the role of the observer, highlighting the interconnectedness of physics and philosophy. By framing these issues in ways that were both precise and conceptually profound, Schrödinger ensured that his work would continue to stimulate inquiry long after his time. Perhaps most importantly, Schrödinger exemplifies the integration of intellectual curiosity, imagination, and ethical reflection. He pursued understanding not only for technical mastery, but for the insight it provided into the nature of existence. His commitment to clarity, coherence, and intellectual honesty serves as a model for scientists, philosophers, and thinkers of all disciplines. Schrödinger's work demonstrates that exploration at the frontier of knowledge requires courage, creativity, and the willingness to confront paradox and uncertainty with reasoned reflection. In the modern era, Schrödinger's influence is evident across multiple scientific domains. Quantum mechanics informs not only physics and chemistry, but also emerging fields such as quantum biology, quantum computing, and quantum information theory. His thought experiments and conceptual frameworks continue to guide theoretical and experimental research, while his interdisciplinary vision inspires collaboration across scientific boundaries. By encouraging integration of disciplines, critical reflection, and imaginative thinking, Schrödinger's legacy continues to shape the methods, questions, and aspirations of contemporary science. In conclusion, Schrödinger's contributions transcend equations and laboratory results. His legacy lies in the profound conceptual framework he provided, the philosophical questions he raised, and the interdisciplinary vision he championed. Through his thought experiments, his reflections on life and reality, and his foundational work in quantum mechanics, Schrödinger reshaped scientific thought and inspired generations of researchers, thinkers, and innovators. His influence continues to reverberate across physics, biology, philosophy, and technology, serving as a testament to the enduring power of deep intellectual inquiry and imaginative reflection. Schrödinger's work reminds humanity that the pursuit of knowledge is not merely about understanding how the universe works, but about exploring what it means to exist within it, challenging assumptions, and seeking coherence, clarity, and insight in the face of the unknown.